Okay, our next talk is by Zaz on the topic of hacking driverless vehicles. Here you go.
Thank you. There it is. Boom. These are some images that I shamelessly ripped off from some American TV show making fun of Waymo. So I'm Zaz. I was on a TV show called Prototype This, which I'm only mentioning because of the driverless vehicles connection. So I have an autonomous robots background, and on this show we did a very early fixed-wing home-built drone for aerial vehicle for dropping life jackets to people in trouble in the ocean. So that's when I learned all about crashing aerial vehicles and having to build them again. So that was about 10 years ago now, before quadcopters took off and became, no pun intended, and became really popular. We also did some driverless ground vehicles for pizza delivery. So this is a two-wheeled, self-balancing autonomous ground vehicle for delivering pizza locally out of that pack you see at the top. And this is a full-scale driverless road-capable vehicle, which did the first ever autonomous crossing of a United States highway bridge. So that's our little claim to fame. And this vehicle actually ended up going on to be the seed that grew into Google's driverless vehicle project. And I also host autonomous vehicle competitions for RoboNation. So I don't think we've had a Serbian team yet in any of the competitions that I do. So it'd be nice to see a Serbian team. We did have a Croatian person on a Swedish team, but hopefully we'll see some full-on Balkan teams soon. I'm going to go really quick through this intro stuff because I did a practice run of this talk and it was way too long for the time that we have, an hour. So I'm just going to skip pretty quickly through some sort of driverless vehicle intro stuff. The reason why we're going to have driverless vehicles eventually is because you save energy because you don't have to move around a human driver. You save time because you don't have to stop for the driver to take a piss, and you can do kinds of things that you would not ever be able to do if you have to have a human on board all the time, just like space probe robots. It's the same kind of thing. So we're not going to stop the revolution. So I'm not giving a talk saying let's hack these vehicles and make it so people can't have them. We want to have nice things, but we want to also find the vulnerabilities and make it so that we can have nice things without people hacking them. Just some quick things about what's happening in Europe, since we're here in Europe, because the Americans, they get tons of press for the driverless vehicle efforts, but tons of interesting things are happening in Europe. We got Nissan testing autonomous Leafs in London since 2017, Jaguar Land Rover doing some testing too, and the government is promising £200 million for a research fund. So that's like, after Brexit, that's like at least 100,000 dinars, as far as I know. Sweden, they're testing Volvo. So this is pretty cool, actually. Volvo promised, in 2017, we're going to start testing autonomous vehicles in Gothenburg with real people in them, taking them places, and they just made it, it's great to see people hit a deadline. So they started in December 2017, and that's going through this year. They're doing an autonomous bus in Stockholm, Germany. Of course, they're very serious about technology, so they're testing 40 vehicles in Munich with BMW, and they have made a promise. So we can call them on it. We can watch what happens. In 2021, they say they're going to sell a vehicle that's electric and does fully autonomous Autobahn driving. So awesome. And also autonomous bus trials. The good thing about autonomous buses is they don't move really fast. So the downside of making a mistake is lower. France is doing shuttles as well, and all important, they've passed legislation to allow testing, and the EU as a whole has this autopilot project, which at last call they said they were going to give 25 million euros to 6 cities to test. So that's pretty cool. And I think robots are great. This is some footage I shot of a autonomous helicopter. This was taken at a naval air station in the United States, doing some testing, and helicopters are really hard to fly, right? They crash a lot, and robots are just really good at flying them. So you see something like this, and it's just hovering there. It's doing a great job. You're like, yeah, okay. Machines should drive vehicles. We should have autonomous systems. But one thing I noticed when I was filming this is there are these two guys, right, that set the whole thing up, and they were programming the mission in and everything. And then when they took off, where were those guys? I noticed they were hiding behind the start cart here, just in case the robot screwed up and went haywire. So it's just like, all right, that's a security mindset, right? It's like we got to plan for when things go wrong. And actually, that particular airframe did crash and destroy itself. Not on this flight, but subsequently. So actually, that's the only one of these that you can see in a museum. You can see it. It's in the Evergreen Aviation Museum in Oregon, because after it crashed, the Navy didn't want it anymore, and they gave it to the museum. Quick definitions for autonomous and unmanned systems. So what we mean is we got no pilot, no human pilot on board or driver, but we totally can have someone off board that's supervising things, like these guys controlling a U.S. Customs drone. Means we can also have passengers on board. That's fine. Obviously, a driverless bus, it's not very useful if it can't carry human passengers. And the military are the ones who have done the most work in the space so far, for kind of obvious reasons. They have a lot of money, and they put vehicles in harm's way, and they don't want people to be shot at. Some quick, just sort of like justification of why we should care about this. It's because once the technology gets working, it's going to be deployed really fast, and we've seen that in the unmanned aerial system space. It's like this graph only goes till 2011, but you can see it's the start of an exponential curve. As soon as this capability was available to the U.S. Air Force, they were flying it basically as much as they could. But this is a funny thing here in terms of ground vehicles. Congress in 2001, they were so excited about unmanned ground vehicles for the military, they wanted 1/3 of the operational ground vehicles in the U.S. military to be unmanned by 2015. So that's an example of a deadline that totally was not hit, right? There are pretty much zero operational ground combat vehicles that are autonomous right now. So, you got to keep these things in perspective. Here's an example of a military ground vehicle. This is a Sentry droid from the Army. And so you can see they've definitely designed with, so it can defend itself and stop someone from attacking it. But I thought this was funny. The whole thing is like covered in kill switches, right? Because it's still in testing, and they want to make sure they can shut this thing off as soon as possible if something goes wrong. So I don't know. I thought it was funny. But I'm not gonna. That's the last stuff I'm gonna say really about military applications, because hopefully, unless we're working in the military, we're not gonna encounter those vehicles too often. But there's lots of civil applications. Transportation's obvious. The ocean is a place that's really suited for robots. It's super expensive to send humans out there. It's not very safe. Ships sink all the time, and underwater, of course, is expensive to do manned submarines. Mapping is tedious and boring, so it's great to have a robot do it. Filmmaking really took off with these low-cost multi-rotor platforms. Now it's like if you got a few $100s, you can buy a quadcopter and go and make movies with it. Tasks that you might not think of, like power line inspection. There's millions and millions of miles of power lines in the world, and they corrode and they need to be inspected. And it's a total pain to send a guy to climb up the tower and go and inspect the power line. So it's better to have a helicopter to do it. And then moving stuff around. So just as important as moving people, a lot of energy and time goes to moving stuff around. So it's cool to have robots do it. In the case of shipping, it's like a really sort of logical place for things to end up being driverless, because for a start, 75% of accidents of shipping is caused because the human driver messed up in some way. So we can be more reliable, and also voyages are long and boring for cargo. But one of the problems there is that the reason you have a crew on a lot of these cargo ships is because stuff breaks all the time and someone has to fix it. And these ships can be like spending months or two at sea. So that's something that still has to be worked out for driverless systems. But if you look at the priorities of the industry sort of support group that tries to push driverless technology, where they think this stuff is going to show up first, right? So where we care about as hackers seeing stuff, precision agriculture. So that means farms that can send robots out to fertilize individual plants, or monitor crops for harvest and stuff like that. That's a tedious and boring job, and people are expensive. So it's a good place for unmanned systems. And self-driving cars. So that's the place that I think we really care about it as hackers, because that's where we're likely to encounter things and where problems are going to be immediately apparent. And anyone that wants to go out there and mess with the system, that's where they're going to find it. And the roadblocks, the reasons why even though we could do this today if we had a whole separate set of roads for robotic vehicles, but we don't. We have to share the roads with human-driven vehicles, and humans are bad drivers and they are unpredictable. So that's tough. And then also, a lot of people are just irrationally scared of sitting in a vehicle that a robot is driving. It's the same way some people are afraid of flying, because even though it's the safest way, if you look at per passenger mile, it's by far the safest way to travel that humans have invented, but some people are afraid of flying and they'd rather drive instead. So this exchanging the safest possible way to travel with like one of the most dangerous, just because of the way they feel. So we have to deal with that. Anyway, that's all the intro material covered in a record 10 minutes, and now we'll talk about the interesting stuff, which is how these systems fail. So gonna first do two little case studies of classic failures. First is an aerial vehicle. This is Boeing's RQ-3 Darkstar. Was originally supposed to cost $10 million in 1994, so I won't do the math, but you can work out that's a lot of money, and then of course they spent a lot more on the prototype. So what happened the first time they tried to take off the prototype aircraft? And this is not as fun of a video as you think it's going to be, because I don't have the footage of the actual crash. That's one subsequently that was successful, but you're just going to have to imagine, instead of it taking off smoothly like that, imagine it suddenly like wobbling up and down at an increasing amplitude and then crashing into a giant fireball on the runway. What happened? Here's the write-up on that accident from the International Journal of Unmanned Systems Engineering. Talks about porpoising oscillations due to a fault in the flight control system. What that fault was all the testing that they'd done at Boeing's test facilities was on a tarmac runway, right? So a poured asphalt runway with no cracks. When they did that first flight, they did it on a slab concrete runway, and so there were little gaps in between the slabs. And every time the vehicle rolled over one of those gaps, there was an impulse into the flight control accelerometers and gyros, and the flight computer wasn't ready for these like sharp impulses, hadn't been modeled, and it overcorrected, and the vehicle crashed trying to take off. So the expectations of the system designers are really critical, and if there's going to be hacks and exploitation of the vehicles, it's likely to happen at cracks, right? At little boundaries between things that were not expected or different sets of designers worked on, stuff like that. Here's another classic failure that I've got better video of. This is from the first DARPA Grand Challenge in 2004. So the DARPA Grand Challenge initially was a autonomous ground vehicle race from Los Angeles to Las Vegas, whatever that is, like 800 kilometers, something like that, through the desert. And so this was the vehicle that was considered to be the favorite for this race. It was Sandstorm from Carnegie Mellon University. And so here it is. You can see it taking off, and you can see that they spent a lot of money on this vehicle, right? They used like a Humvee chassis, and they put sensors all over it. They even developed some new LiDARs and stuff for this vehicle. And it was just like, yeah, this is the vehicle that's going to win, right? Well, it got about 7 miles, I think, from the start, in an 800 kilometer race, and it ran off the road and caught fire. Here you see it running off the road, and it was not designed to be at that attitude that it's in, and it caught fire. It was a total disaster. And in fact, the whole race was a total disaster, because that was the vehicle that got the furthest in the whole race. Most had trouble even leaving the start. So DARPA was very embarrassed. It was just like, because there was $1 million prize for winning this race. And so what happened here? Well, I talked to the people who worked on Sandstorm, and they said, well, DARPA really wanted someone to win, right? So they gave us the night before the exact route because that was a secret until like shortly before, because they wanted the competition to be hard. But the night before, they said, this is going to be the exact route. So they went and GPS mapped it. The thing was, they had to decide at certain points, like, do we just follow GPS and have all these waypoints, which we definitely know we can do, or are we going to like try to listen to our other senses and stuff like that? So they decided, we're going to sort of balance one sensor versus the other, and the robot's going to decide at each point like which one, based on how certain it is about certain information. And the robot was just too certain on that curve about how sharp the curve was, and it was listening to one sensor more than it should have, and it ran off the road, even though the road like is super obvious in front of it, and they had GPS information and everything. So the moral of the story there is just deciding what the robot really knows is a constant battle. You know, it's got all this information coming in. How reliable is that information, and what's real? So that getting that state estimation right is key to decision making. And if we're going to exploit, in a hacking sense, a driverless vehicle, then we need to subvert that state estimation process. And conversely, from the designer's perspective, you need to make sure that that state estimation process is super robust.
Do you believe the robot would have made it if they didn't put the GPS?
Yeah, that wasn't even a difficult curve. I would have made it all the way.
Yeah. What if it's 70%?
It's hard to know. I mean, it's just clearly the system was not robust, right? It was like, that's not a difficult curve to navigate. So
Maybe you could think they messed up just adding the GPS.
yeah, it could have made it, but making it wouldn't have proved much because we can see that the whole system was really fragile. So the logic underneath any of these systems has these kind of hierarchical, or we can arrange the logic into these hierarchical structures, where we have at the bottom control loops maintaining stability of the robot or the system at any time. Above that, collision avoidance, sort of the most important thing. Once we have something that can drive or fly, is to not run into things. Above that, we've got our navigation system. So if we can go from point A to point B without running into something, the next step is like we want to go from the right point A to the right point B. And then finally, whatever runs on top of that in terms of high-level mission planners, and you know what's the vehicle supposed to even do. In the case of a bus, navigation is basically the top level, except you still have to open the doors to let the passengers out, and you have to maybe check tickets and stuff like that. So that's where that would be in a bus. If you attack anything at the lower level in this stack, everything above is defeated, right? So the bus can't let the passengers off if it's already crashed into something, and so that means that it's a juicier target to go down low in the stack, but also more engineering effort usually gets expended there. So the lower levels are usually more robust. So you got to trade that off as an attacker. So just some quick examples from the ones that I mentioned right at the beginning from prototype this. So the life-saving drone at the bottom, so there's a fixed-wing aircraft, so it doesn't have to do a lot of stability maintenance, but it does have to be able to fly straight and level and to be able to turn and stuff like that. So you have your PID loops that are tuned for the environmental conditions you expect. So there'll be a maximum amount of wind gust, for example, that these control loops can deal with. If the wind is blowing intermittently faster than that, then you're going to have a problem. No collision avoidance at all. So this plane will happily fly straight into a tree. In fact, it did twice. So that's just one of the weaknesses of the system. Navigation was done with only GPS. So just going through a circuit at various waypoints. And then the high-level mission is to drop the package, which is a self-inflating life vest. And so that meant that as it gets close to the target, it set up this dynamic bombing run to make sure it was coming in perfectly straight and level, dropping the package where you want it. So from an attack perspective, this vehicle is extremely vulnerable to collision. If you put something in front of it, it will run into it. And its high-level logic depends on that single sensor. So if its GPS has a problem, that vehicle cannot do what it's supposed to do. For pizza delivery, I'll just use one of them, which is the local pizza delivery, because it does have the interesting stability maintenance. That's a two-wheeled self-balancing platform. So at the low level, it's just staying upright. If it falls over, it's done. It can't pick itself up. So it has to make sure it doesn't fall over. Collision avoidance is all done dynamically. So it has a scanning sensor that lets it detect dynamic obstacles and make sure it doesn't run over a dog or a person. Navigation, not done with GPS. It's all done from a SLAM-generated map. SLAM is simultaneous localization and mapping. So it's sending out, uses a laser, a scanning laser, which we'll talk about in a bit, to sense its environment, build a map, and then place itself on that map. So it can, it means if it does find itself in a place it's never seen before, it has no idea where it is, but eventually it'll build a map. And then at the top level, it's like the bus. It gives the pizza to the person who paid for the pizza and tries to stop someone else from taking the pizza. So it's vulnerable to all the kinds of things that a vehicle with a dynamic map is vulnerable to. right? So if you can confuse it about where it is on the map, or if you can use dynamic obstacles to force it to move off the map, then it doesn't know where it is. That's the main vulnerability. Also, you could totally kick it over and steal the pizza. It's true. Sad, but true. Within the high-level logic, it's usually some kind of mission-oriented state machine. So the states usually correspond to subtasks, especially if it's a vehicle that has to do multiple things. And then the transitions between those states can be task completions, or perhaps task failures if the vehicle is able to detect when it's failed at some task, or maybe even just a timeout. And then within a state, you can have sub-state machines and so on. So these systems can get pretty complex. But in the case of a bus, for example, it's not that complex in terms of the mission. You go places, you open the doors, you check tickets, that's about it. So vulnerabilities here could be in the state estimation process again. That's if you confuse the vehicle as to what state it's in, if you make the bus think it's at the stop and it's not, and then transitions between the states. So you can either spoof those state transitions or prevent the state transitions from occurring, or for the vehicle from realizing that it's successfully done a state transition. And then you can make conditions be unexpected within the states. And the primary way that we confuse any vehicle is by the things that it uses to see the world around it, which are the sensors. Sensors come in two different categories. Active sensors send out information and read it back, like a radar, and passive just take in information from the environment without sending anything out. So I'll run through the list of sensors that are pretty common. The GPS, of course. If you're above water, you can use GPS, or if you're not inside a building. So driverless cars usually have 2 GPS units, so they can do differential GPS. And they work great except when they're in a car park or a tunnel. LiDAR is like radar but for light. So it's a laser rangefinder basically, and usually now on vehicles you see these spinning laser rangefinders, and they're normally on top of the vehicle. Cameras, of course. Cameras are super cheap now. You can afford to stick them all over your car, and manufacturers increasingly do. Millimeter wave radar is now common for collision avoidance, usually on the front and back of a car in the bumper area. Ultrasonic transducers send out ultrasonic pulses and get them back, and it's an active sensor, and they're often used for parking. Digital compasses are important. It's nice to know which direction you're facing. And then inertial measurement unit, which is made up of accelerometers and gyroscopes, which tell you information about how your vehicle is moving. On cars, you often have wheel encoders because that's one of the best ways to do odometry. You can do odometry with GPS. Odometry meaning like how far you've traveled in a given time. But if you're in a tunnel, if you're in a parking garage, stuff like that, I can't use GPS. So it's nice to have that like really accurate, this is where the car is moving information. And then specialty sensors for other applications. For example, underwater, you'll have usually a Doppler velocity logger, which is an acoustic sensor that sends out pulses to reflect off the bottom of the ocean or the lake or whatever you're in. And that also is for doing odometry. It can tell you how fast you're moving, and by subtracting how fast you think you're moving from your thrusters versus how fast you are compared to the bottom, you can tell what the current is. That's very useful. And scanning sonars, sort of like the LiDAR for underwater. And then pressure transducers, both in the air and underwater, to tell you your altitude or your depth. What makes sensors information uncertain is primarily noise. So that's the definition really is what the difference is between your reading of the environment and what the real truth is in the environment. And then also drift. So that's how much the sensor value, in the absence of any change in the environment, how much it will change. And then another thing that's important is just what your latency and your update rate is. If you've got a GPS and you're only getting a reading once a second, then that means how far you are away from where you thought you were depends on how fast you're going. And so often you can, that's what can make it difficult to get an accurate heading with GPS, because if your latency is high And you've also got some noise, of course. You can have your heading be the reverse of what it is if you are moving slowly and you're not getting a big difference between your GPS signals. So that'll depend on how fast you're moving and what your latency is. And so you model your uncertainty to try and make your system better, but you make certain assumptions. And so those, if you're trying to hack a vehicle, then you've got to look at what assumptions might have been made when they're modeling the uncertainty in their sensors, and then you can try and exploit that. It's great having multiple sensors and fusing that information together. That can be more useful than having separate ones, but as we saw with the sandstorm example, what do you do when your sensors disagree? That's really important, because the robustness of your robot may come down to just how good is it at discounting the information from one bad sensor or one sensor that someone else is trying to mess with. There are two basic kinds of attacks on sensors. You can DOS them, right? So you can make it so they don't give useful information at all, or you can spoof the information they receive. So that's deliberately causing the sensor to get some data that's incorrect the way that the attacker wants it to be incorrect. And then you've got a couple of choices about your attack mode. You can either sort of instantaneously give bad data to the vehicle, so try and make it make a bad decision in the moment, or you can slowly give it bad information, so it builds up aggregated bad information. So you can convince it its sensor is drifting, but it's not really, or you can make it build a bad map, for example. So we'll cover all the different sensors and their attacks. So GPS denial is super easy because GPS signals are incredibly weak. They have to come from space, and so the only reason GPS works is because we can craft receivers that are very good at picking up specific information they're looking for. So to jam it, you just throw a bucket of RF noise at it at the GPS frequencies. You can buy a GPS jammer from sketchy websites in China for like about $15 or something because they're simple. You can build your own. The schematics are available online, so if you've got a spare afternoon that you're bored, you can always make a GPS jammer. Of course, you should only test it in a closed room so you're not interfering with people out on the street. And then a spoofing is also pretty similar. You just fake your GPS satellite signals at a higher power, and the target system locks onto your signal instead of the real signal, and then it thinks it's in the wrong place. So here's an example of doing that to a UAV. This is from UT Austin's Radio Navigation Lab. This was kind of the first group to do GPS spoofing sort of and announce it to people that they were doing it. So what you can see here is they're trying to, in this animation, they're taking over an aerial vehicle by moving their signal exactly onto what the vehicle sees, and then they're shifting their signal in some direction, and they're expecting the vehicle to compensate by going in the other direction. So when we see the live demo, what they're going to do is, or the film demo, they're going to try and trick the helicopter into thinking that it's going up. And so the helicopter is going to compensate by going down. And as long as you keep telling it's going up, it will eventually fly itself right into the ground. So here it's being controlled by an off-board controller. And now they're sending the spoofed GPS signal and they're telling it it's going up. So it's going down to compensate. And if the safety pilot didn't take over, it would have flown right into the ground. Which is what the Iranians claimed that they did to an American drone in, I think, 2016 maybe. They captured this AQ, I think the Iranian TV is wrong here, I think it's an AQ-7, but they claimed that they spoofed GPS and flew it into the ground. That's probably not true because the US military totally knows, same as all of us do, that GPS is very spoofable. So GPS is never used as a primary sensor for military systems. It probably just crashed by itself, but anyway, that's what they claimed. In the civilian realm, actually, hang on, let me go back for a second. In the civilian realm, GPS usually is the primary sensor because it's usually pretty reliable, it's easy to deal with, and so we can use GPS to basically determine where we are on the map, and then we can just do the collision avoidance and the last few meters with our LiDARs. But you can still see this causing problems. So what to watch for here is, this is from the second DARPA Grand Challenge. So the year after, DARPA was super embarrassed. They were like, all right, we're going to up the prize money to $2 million, and you guys better do it properly this time, right? And so more universities competed, and the team from Stanford ended up winning. Their vehicle was an autonomized Volkswagen called Stanley, and it still had some troubles. It made it the whole way. It won the race, but watch this short clip showing it driving down a super drivable road, right? It's like very obvious where the road is, but it's like trying to drive off the road into the bushes for no reason whatsoever that you can tell right looking at it, right? So why is it doing that? So without looking at the logs, it's hard to tell for sure, but to me, as an observer watching this, that's classic behavior of a disconnect between the GPS and the instantaneous sensors. So the GPS is trying to drag it slowly. You know, when you set up a GPS track, you don't want to write a controller that goes bananas if you're not exactly on the track, and you don't want it to turn 90 degrees to get back on the track. You write a controller that's going to nudge itself back to the track. So it's like drifting back to what it thinks its GPS track should be, but then the LiDAR is saying, hey, wait a second, there's like the road's right here, dude. You know, so it's like struggling, like GPS is dragging it left, and the LiDAR is saying, no, come right. Sort of classic behavior. Another one that is pretty funny from the DARPA Grand Challenge. This is just a vehicle just trying to get out of the starting area, and so it's just doing straight up GPS nav, and it completely fails to notice this Jersey barrier and drives right over it because the GPS is just saying, drive in a straight line, you know, but their track is not quite correct. So, you know, the coolest thing about that for me is like, who knew a van could drive over a Jersey barrier? Like you'd never try that in your own vehicle, but it's cool to watch the robot do it. The UT Austin people also decided like, oh well, now we did some like janky $1,000 helicopter that no one listened to us. So what about if we took over something that was really worth a lot of money that uses GPS guidance? So they found some guy that owned a mega yacht or a super yacht. I don't know what the difference between a super and a mega yacht is, but it's like either way, these things cost tens or hundreds of millions of dollars. This one's called the White Rose of Drax. And the owner was like, oh yeah, someone could like, are you telling me someone could steal my like $100 million yacht with a GPS spoofer? Yeah, I'll let you like give it a shot. So they got permission. This is the animation of what they're doing. Very much the same as the helicopter, except in this case, they're going to give it a GPS signal that's going to adjust the heading that the boat sees itself doing by just a very small amount, by 3 degrees. And so the boat's going to correct its track, or think it's correcting its track, but really it's going the way that the attacker wants. And the reason this works, or this would work if you hadn't asked for permission from someone, is when you're out in the middle of the ocean, there are no other navigational references. GPS is the only sensor that's being used. There used to be other types of ways that ships did navigation, but no one's pulling out their sextant anymore. And even the LORAN system, which was a previous radio frequency navigation system, that was turned off some years ago. So you're out in the middle of the ocean, GPS is what you got, and there's no way to tell that you're being faked out because you can't refer to anything else. And so you can see the radar track here from that test showing, yeah, they were pulled off course. And 3 degrees doesn't seem like a lot, but if you're going thousands of kilometers across an ocean, by the time you get to the other side, 3 degrees puts you a long way away from where you thought you were going to be. And the hardware cost for doing this at that time was $2,000, right? So economies of scale, right? You got $2,000 for the hacker versus $100 million for the boat owner. And so lately, that price has been dropping even further. So one of the first groups to publish a homebrew GPS spoofer was this China Qihu 360 Unicorn team at DEF CON 23. And they used a Blade RF to make a low-cost GPS simulator, and they POC'd it by going to like automotive showrooms and convincing the car's navigation system that they were in the middle of a lake somewhere. And that's costs what a Blade RF costs basically, which is like $500, $600, something like that. And now it can be even cheaper. And so there's like this is now no longer new, right? DEF CON 23 was 3 years ago. People do this kind of stuff all the time in talks, and they show videos. I thought it would be cool to actually do it live and see if it works. So I've sacrificed a goat to the demo gods earlier today, and we're going to see if we can take over a UAV. What I'm going to do, I've got a SDR hooked to a Raspberry Pi over here, and we're going to try and convince. We got actually two vehicles here. We're gonna just so we got a backup. They have a built-in collection of no-fly zones. So we're gonna take off the vehicle and we're gonna try and convince it that it's in an illegal flying location. And if you guys can play along, if you've got a phone with a GPS, turn off all your assisted GPS, turn off Wi-Fi, turn off cell signal, and just run your maps in GPS mode, and you'll be able to hopefully see where we're telling the drones they are. And hopefully we're going to trigger their auto landing, saying like, all right, we're in an illegal no-fly zone. We're going to land. And don't totally stare at your phones, because if it goes nuts and goes towards you, block your face. So first we'll take off, and then I'll start transmitting our signal, and we'll see if we can force at least one of them to land. And we have done this successfully, so you have to trust me if it doesn't work, but hopefully it'll work. So we're just going to take off and hover, because we don't want to give it the fake signal until now, because otherwise it won't take off at all. So now we're sending out the fake signal. I'm gonna double check on my device and see if it's working. And yeah, if anyone gets the location, shout it out. So my map shows us as being in Serbia. I'm sorry it's backwards, but that's just the way life is on this video. Anyone get the signal yet? Someone got it? Yell it out. Which airport? Yep, so we're here at, I know it's hard to read, but we're here at Nikola Tesla International Airport in Belgrade. And that's definitely a no-fly zone. We're right next to the runway. We shouldn't be flying our drones there. So how are we doing on satellite pics? Frustratingly, we found that these drones are kind of robust, at least to the signal that I'm sending out, and so they really we've got 11 satellites fixed right now, and they should be coming in, but they just need an exact fix. We found it was easier. Possibly there's a lot of interference from the motors, because we found it was easier to convince them they were in a no-fly zone before they took off than to make them forced land. But forced landing is more fun, so we decided to go for broke here. I guess we'll give it just a few more seconds and see if we. What have we got here? Oh, we've got the auto landing. I didn't get on there in time, but it said no-fly zone detected, auto landing in 15 seconds, and then it counted down and landed. So, all hail the demo gods. Huge thanks to Tomer and Kost for giving up their time and their battery power and putting their drones at my disposal here. So let's give them a big hand for helping out. So yeah, I mean, it's not the most exciting demo in the world in terms of like instant gratification, but for $300 in investment, you know, it's not bad. You can knock a drone out of the air sometimes. All right, moving on from GPS. LiDAR is, of course, the laser range finding. So it sends out, it's an active sensor, sends out a laser, and usually onto a spinning mirror, so it can scan across. So what you get back from your LiDAR is a big line of 3D point returns. And so then you can take your line scanning LiDAR and you can knot it up and down, and so you can get sort of 2 dimensions of scan there. Or now you can get these multi-beam LiDARs that will give you like 8 or 16 horizontal bands of these points. So what you get back from your LiDAR is a point cloud, and you can use that point cloud to do obstacle avoidance and map building. So that's an example there in the video of what your point cloud looks like, and it's totally up to you to process that. Those points are all totally doesn't give you any connectivity information or anything like that. You're up to you to build a convex hull or something and decide what you want to do with it. So DOSing a LiDAR is pretty easy. You just have to actively overpower the return signal. So you figure out what frequency it's operating at, and you shine back a laser back into it, and it won't be able to see its returns. And then you can spoof a LiDAR by either manipulating the environment, so you can make things that absorb or reflect differently than how they should, or you can actively spoof and send crafted laser pulses back to the LiDAR. Here's an example of what we're using a single 2D LiDAR for the pizza delivery. So you can see the pizza delivery vehicle crossing the street here. And because it's this self-balancing platform, if you sort of watch the way some of these strings of returns extend out and come back, that's because when the robot changes its angle of lean, it's hitting the ground at a different location. So that means a steep incline can look like an obstacle, or something that's underneath the LiDAR. Of course, it can't see it, and it'll run right into it, like a curb. And so there's actually I don't have a copy of the video, unfortunately, but there was a funny sequence here where that drove straight into a curb and just, bam, fell on its face. LiDAR is active emission, so it can only see what returns a signal to the unit. So if it doesn't get anything back, it has to assume there's nothing there. So if you're processing LiDAR data as the vehicle designer, you have to accept that most of the world returns no data at all. Everything above the horizon, everything that's out of range of the LiDAR gives you back nothing. Things that are absorbent also look like nothing. So, you know, you do your Wile E. Coyote thing and you paint LiDAR absorbent material on a wall, the vehicle would think there's a hole there and that it could drive right through it. Transparent things let the light through so they don't give you a return. LiDARs are getting better about that, and now you get multi-return LiDARs that give you some transmittance information, but they're still not perfect. And then finally, wait, there was supposed to be a picture here. No, I don't know where it went. Things that are reflective confuse the laser because, like a puddle on the road, for example, your pulse goes out, it bounces off and goes somewhere else. So if there's something else far away that makes a return, suddenly it looks close. So you can see reflections and confuse the vehicle that way. Or if it's something absorbent and it doesn't return, it looks like a huge hole in the ground, right? So when the vehicles are programmed using LiDAR as the drive versus don't drive sensor, if you have a patch in the middle that returns nothing, it just assumes there's a huge ditch, and if it's big enough, it won't drive into it. This is just a funny thing that I picked up that's like slightly relevant because I like to, you know, find interesting things on the dark web. This is a document from an Al-Qaeda offshoot in Mali, in West Africa, and it's got a bunch of, like, basically, you know, how to fight the Americans details. This part here refers to a GPS jammer, a military-grade GPS jammer that they've been using from Russia called the Rakal. And then this is talking about using reflective materials if they have to. They know that they're vulnerable when they use vehicles, so they put reflective materials so that if someone fires a laser-guided missile at them, that maybe the designation spot won't show up well on the vehicle. But reflectance actually is used by autonomous vehicle designers for things like road line detection. Because you've got this road, it's returning a great signal from the LiDAR, it's like very dense point map, but the road the painted lines and painted markings on the road are reflective. So they show up as black, no return zones. So you can actually stitch them together and you can find the lane markings and stuff like that. So that means, just like with automated license plate readers, which you'll hear about in a talk later tonight, if you attend, you can make things that are visible to the vehicle but are invisible to the humans, like the police, for example, right? So you can paint things on the road that are black on black that will be LiDAR reflective. So, for example, a human sees a normal road, but the robot sees like swervy lane markings and has to drive in a weird way. Or maybe you could just put messages on the road for the people at back at the maps location to read when they go through the maps. Things that look solid are solid. The LiDAR doesn't know if something's soft or hard, so you can make a very lightweight, soft thing that looks like a giant boulder. And denial, you can overpower the LiDAR. So this is results from a paper from KAIST from last year, where they pointed lasers at LiDARs, and you can see this is a multi-return Velodyne LiDAR. So you've got I think this is an 8-line spinning Velodyne LiDAR, and there's an obstacle in that area, and by shining a laser at the receiver, they make it look like the obstacle is not there. So if the vehicle was driving into that spot, it would run into it. One thing that's like the same research came up with that's like super interesting and you wouldn't necessarily think of is that you can cause false returns using a laser that's not strong enough to completely overpower the sensor. It's a little bit weaker, But because all of these 360-degree LiDARs use curved glass, you can hit that glass at an angle and it will refract into the sensor and it will make a false return appear not where you are and not in between you and the vehicle, but somewhere else. So for example, you could be driving by the vehicle, hit it with your spoofer and make it think an obstacle is in front of it, even though you're next to it. So here's some real examples. This depends on the source strength. So a weak signal hits the, this is like, can you guys see those dots? I can't see them at all. The first one, there are some dots in between the attacker and the sensor. In the second one, the fake dots are not in between, so off to the side. So you can craft where you want your fake obstacle to appear. That's a pretty interesting result. You can also do a relay attack, and the timing is really crucial here. So what you do is you watch, you characterize the pulse rate and frequency of the LiDAR you're attacking, and then you send pulses back in advance of the new ones coming in, because these pulses are very predictable in terms of when they come in once you characterize it, and then you can send these ones back. And so what you can now do is induce fake dots at any distance between you and the LiDAR. So here there's one inducing fake returns further away from the spoofer, and here we're inducing a fake obstacle in between us and the spoofer. So this obviously is a pretty difficult attack to pull off, because you've got to be listening for long enough to know exactly where the LiDAR is. Like if everything's moving, it could be pretty tricky, but it's a theoretically possible attack that's quite versatile. So that's it for LiDAR. This is just a quick slide from Tesla's website about what their autopilot system uses. So that's probably the most common, not fully autonomous, but sort of supervised autonomy system that's on the market today. You can go and buy a Tesla. You'll have to wait if it's a Model 3, but you can buy a Model X right now. And it'll have this autopilot system. Doesn't use LiDAR at all. It mostly uses cameras, and it also has a radar that looks out further than the cameras do, except for this sort of narrow forward one, but the radar is 160 meters out for collision avoidance. And they also have ultrasonics for parking. So just quickly on cameras, usually used for specialized object detection. So Tesla's autopilot is looking for other cars on the road and for pedestrians. You know, the kinds of obstacles you'd find on a highway in a bad situation. In the lab, vehicles under development, we often see stereo camera systems used, but they're not prevalent in deployed systems right now. They give you a depth map, but these days if you're testing and you have 8,000 to spend on a Velodyne, you'll buy a LiDAR instead of using stereo. But ultimately, something like Tesla, who wants to keep everything really low cost, they might move to stereo cameras. One use of cameras that's really common is what's called colorizing the LiDAR. So what that means is you've got this point cloud, you register that point cloud with your camera field of view, and you give a color, a real world color to all those points. And that lets you do some sort of coarse, like vegetation versus non-vegetation detection, or road versus non-road. So this is from Stanley, the one I showed you before, almost driving off the road, from the second DARPA Grand Challenge. It used colorized LiDAR and color-based prediction to drive fast. The way that they won was just by driving really fast most of the time. So what they do is they use the LiDAR to map the road and say, okay, this surface looks good and this surface doesn't. Now let's look at everything that's the same color as the good surface, right? Because these dirt roads are not the same color as the vegetation. So now we can predict further out and we can drive at speed. So that's a really useful technique. But it also means that color is being given a lot of importance, and color is like super easy to fake. To deny cameras, very easy, just shine a bright light at them, they can't see anything. And to spoof them, everything that works on human vision, camouflage, making assumptions about color, and in the case of stereo, repeating patterns confuse them a lot. I mention it because it's new research, but it's not super applicable yet to driverless vehicles, which is adversarial attacks on computer vision AI. Hand? With cameras? Yeah, a lot of the cameras they use for in darkness are infrared sensitive, so that they can still see a lot. The Uber accident that they had recently was an interesting case because it ran into a pedestrian and killed the pedestrian. The safety driver was not paying attention, and so it looked bad for Uber, and so they sent out all this video that were like, oh, our cameras couldn't see it, and so they sent out all this video where the levels were really low and everything looked super dark, but other people drove on that road at the same time of day with their own cameras and like compared the footage, and it looked great, because there were street lights, the cameras are infrared sensitive, so Uber basically had put out these like artificially darkened images to make it look like it was harder than it really was. But the cameras these days, cameras do okay at night, especially the ones that are infrared sensitive. This stuff I'll cover really quickly because it's not that relevant, but for completeness. So there's this super famous paper where these guys crafted adversarial stop signs. So they trained a deep learning model on stop signs, and then they put just black and white tape on it, and they could convince the vision system that the stop sign wasn't there. So obviously, this is the kind of like visible to the robot, but not the police kind of situation. The police see the stop sign is still there, so that no one does anything about it, but it fools the robots. It's not really as robust as you might think from the paper. But anyway, it's there. Here's another example. This is even more of a lab model. So they trained up a pedestrian recognizing system, and then they found by crafting adversarial noise and adding it to the image, they could convince the vision system that there were no pedestrians there. So you totally can't see this on the slide, but there's just it's very difficult to see even like when you've got the image on a regular monitor, but there's just some fine colored noise in that image, and that tricks the deep learning system. So that's like sort of one sort of adversarial example is to convince the system that it doesn't see something that is there. The other is to have it see something that's not there. These are generally, so far in the lab, these white box techniques, so the researchers make the deep learning system, they know exactly how it works, they know how to trick it. In the case of adversarial noise to the camera, if you're on the car's internal network and you can inject noise into the vision system, you've already owned the vehicle. You don't need to make it miss some pedestrians. And parametric distortions often really mess them up. Just if the car's at a different angle or the lens on the camera isn't exactly what you expect, it doesn't work. Here's one that is actually quite robust. These guys developed these adversarially perturbed models and then 3D printed them. Well, the textures are 3D printable, so they could 3D print this turtle with a special texture on it, and then the system that they'd trained on various objects thought the turtle was a rifle instead of a turtle. And it was robust to moving the turtle around. It was a physical object. You could throw it on the ground, and the system would say there's a rifle over there. So that's pretty funny, but still not super relevant yet to driverless vehicles, but it's interesting. The radar is a sensor that's like pretty easy to mess with. For those who don't know about millimeter wave radar, that's what's in the machines at the airport that let the security people see your genitals. And they primarily used for collision avoidance because they're kind of a coarse sensor. They're low resolution, and most things are very reflective to the laser, so to the radar. So the radar sees stuff everywhere, so you normally double check it with something else. But in the case of the highway for Tesla Autopilot, it'll say, all right, there's a big thing in front of me here. I'm just not going to run into that. You can jam the radar. You can use the same thing that in the military they use to get radar guiding missiles away from you. Use fine reflective chaff, and then overhead signs screw up the radar. So the return from a big flat piece of metal over the road is so big it can't see something underneath. So if you have an obstacle that's underneath an overhead sign, if the only thing the car is using is a radar, it won't see it. Here's some examples of real-world, POCs of attacks. So this is from DEFCON 24, contactless sensor attacks. So they successfully were able to jam the radar on a Tesla so that it couldn't see an obstacle right in front of it with the radar. All you need to do that is $100,000 worth of RF equipment. So you're in the same price range as the Tesla itself, probably more expensive. They also theorized spoofing and relay attacks, but didn't perform them. The IMU and the compass, that's the inertial measurement unit. those are super robust, and that's why military systems, underwater systems that can't use GPS, they use them as the primary navigation sensor. And you can get super high fidelity models, so like 0.1% of the distance traveled. So that means, like if you get an IMU from a Boeing 777 and you take it 300 kilometers, at the end your distance error will be 300 meters. So very, very good, and that's why they use them for like underwater robots that go under the ice for months. Very difficult to interfere with. If you can get close to them, you can use magnetic field attacks. You can take advantage of thermal drift by heating them up. But if you can't get right on top of them, you can't really do much to them. With one exception, recent attack from this year, I think. I'll add my things here so I can see when it was. Oh, 2015, sorry. I only found it this year, but I thought it was pretty cool. This is a variation of the shouting in the data center attack that you might have heard of. Hetty mentioned it in his talk yesterday. Because MEMS gyros, so cheap gyros, not the kinds you'd find in a Boeing 777, but the kinds you'd find in a quadcopter like that, they have a tiny moving part inside the chip. And so if you can resonate that at a physical frequency that's similar to what it's trying to read, then you can jam it. So you can do that with acoustic noise. So these guys took a quadcopter, they pointed a loudspeaker at it, and you can see on the right here, when they turn that speaker on, they just fritz out the control system. It can't get any gyro information, and the UAV crashed. So again, you have to get pretty close to do an acoustic attack on something. But if you had a small installation you wanted to protect against cheap drones, that could be a way you could do it. Wheel odometry. Second to last sensor here, coders on the wheels. This can make a robot stop. So this is our pizza delivery vehicle from prototype this, the full-size vehicle, and oh, what's happened? It's like going into the wall here, and suddenly it stopped, and it's spinning its wheel, and it has no idea what to do. And what happened is it scraped its wheel encoder off on the wall. It took the curve a little too closely, scraped the encoder off. Suddenly, it thought it was driving, but it wasn't getting a signal from the wheels. It didn't know what to do. So that's an easy attack to try and scrape it off. You could also, if you've got physical access to a vehicle, you could change the wheel diameter so it thinks its speed is wrong, or you can make it slip, stuff like that. Final sensor is the ultrasonic sensors, which are mostly used for parking at low speeds. So there's it's a low impact attack, but this was successfully both jammed at this DEFCON 24 one, so you can see both a Tesla and an Audi not seeing an obstacle that's there, and then here spoofed, making it show an obstacle. By sending your own chirps, you can make it see an obstacle that's not there. And then you can also do a cancellation attack if you know exactly when the chirps are expected to come back to the system, or expected to come to the target. You can send out a chirp at that same time and do wave cancellation. And I know I'm hitting the end of my time here. I don't want to cut into the lightning talks, which are coming up next.
I need more time to prepare.
Oh, okay. All right. Well, I got my warning from over here. So as soon as you're ready to drag me off the stage, just scream at me from over there, and I'll finish. The map is a super important part of the driverless vehicle ecosystem because it makes your whole job so much easier. So one of the reasons why driverless vehicles are becoming a thing now, and they weren't 10, 12 years ago, is because Google hadn't built up a huge amount of map data then. Google were really the first ones that said, okay, it's feasible for us to build super high fidelity LiDAR maps of the entire country, for example. And so then we just know where everything is. It makes life so much easier. So they often use it to be the reference ground truth. If something's on the map, it's real. If it's not on the map, it's an obstacle. It's something that we have to avoid. So that makes it much easier for the vehicle. Things like traffic lights, for example. Traffic lights are super hard to detect a priori because they're just a colored thing, right? But if you know where all the traffic lights are, you know exactly where to look, and then you just have to check the state. Is it green? Is it red? And that's how Google actually does it. Other things are vegetation. Vegetation's messy. It's green, sure, but it's all over the place, and it doesn't stay the way that you put it, right? It grows. So if it's on the map, you can say, all right, that thing over there, that blob, we don't know exactly what it is, but that's where we have a tree on the map, so that's a tree. And then, all kinds of other things like that. If you know like where the speed limits are, then you don't have to detect speed limit signs. But that means, yeah, so here I got the traffic lights, camera knows where to look, and that means there's a difference there, right? If you can do things that the robot doesn't expect based on the map, that can make it easier to do a confusion hack of some sort, right? So it's the same thing about stuff that a policeman can see but the vehicle can't. If you put up a fake traffic light, everyone else is going to stop at that traffic light. They don't know if it's real or not, but the robot is not going to see it at all because it's not on the map. So if you're pulling up at an intersection and you see there's a red light in the other direction and you're green, you're going to go through it. You're not even going to think about it. But if coming the other way is a driverless vehicle that doesn't know there's a traffic light there, doesn't see that red light, it's going to blow straight through that intersection and maybe crash into something. Here's about vegetation, using a transmission classifier with colorized LiDAR. But last time I rode in Google's car, it got really confused by a tree that had grown and was hanging over the road, right? It had the tree on the map, but it had grown into the road, and it could have driven straight through it. It was just vegetation, but it didn't know. It was just like, what is this thing? It's like, we don't know how hard it is. It could be an overhanging piece of metal, you know. So dependence on the map makes these discrimination rules even more brittle because you don't have to put so much effort into making them work. And the map also requires constant updates, right? Things change all the time, and if you don't update your map, then you're going to make bad decisions. But now you've got an attack vector, because if there's a local map on the car, then you can put unexpected features, and it's not going to necessarily have done its update yet. But if it's constantly querying the remote server and working off a remote map all the time, then you can do your denial and spoofing on its map update process. And in general, if you really want to attack one of these systems, you want to maximize its uncertainty again, like interfere with its state estimation. So find places where it's already at the edge of its uncertainty. Okay, so one of the most difficult things to do when you're programming a driverless ground vehicle that has to operate in traffic is doing a right turn. This is in the United States, right? We're driving on the right. When your vision is blocked by a car to the left. So what do you do in that situation? What a human driver does is they inch out and sort of look past the car, and they have some sort of knowledge about what's going on in the world around them, some contextual knowledge. They know what time it is. They know how busy the road is. They can also listen. So you kind of figure it out, and you go out a little bit, you know. Whereas the robot has to play it really safe, and so sometimes you can trick the vehicle. And there's been a bunch of these cases in San Francisco where they're doing a lot of testing, where people got really angry at the testing vehicles because they would never pull out in this situation. They would just sit there until there was nothing blocking their view, and then they would go. But that holds up traffic and makes people mad. So one of the attacks you can do is like confusing and annoying people on the road or people in the vehicle just by making the robot be super cautious, or making the safety driver have to take over, inconveniencing other users on the road. And if it's a super fragile maneuver, you might be able to trick it into pulling out and getting T-boned like that. Which I've got a funny story about. I was talking to this bus driver late at night the other night, and there was no one else on the bus, and the bus driver was like ranting to me, and he was talking about how much he hated Uber drivers. And he said that whenever he was next to it, he's like, "They're such bad drivers." He said every time he was to the left of an Uber driver, and they were like, you know, pulling out into traffic, but he was blocking their view, he would like wait until the light was still red and traffic was coming across, and then he would move the bus forward, you know, like a couple of meters, and so the Uber driver who wasn't paying attention would think that the light was green and would start going into the intersection, and then they'd get in accidents. So I'm like, dude, that's not like a really kind thing to do to people on the road, bus driver, but he thought it was really funny. And you can I'm sure it's easy to trick the robot to do the same thing. I mean, it's going to be looking at the traffic light, but in these other type of intersections which aren't controlled by things that the robot can sense, if you know where to block its view, you can probably make it make bad decisions. And of course, if we want to do physical attacks, if we have access to the vehicle, we have the advantage that we also can use sensors, right? So we can attach things clandestinely to a vehicle we want to mess with, and we can then make our attacks take place at a time and circumstances of our choosing. So we can put a GPS in our electromagnet, and we can put it near a car's digital compass, and then we can only turn it on when we want to confuse it, or when it's in a location that's confusing, or we can have it triggered by certain locations on the map or something like that. Two of the ways that we probably most likely, or bad people, not us, bad people would most likely mess with a driverless vehicle would be to make it get trapped, to get into a location, so attack it at its collision avoidance and navigation layers, so get it into a position it can't get out of, and force it to postpone what it's trying to do, right? So in the case of the pizza delivery robot, if we want to get it somewhere where we can like attack it and we can open the pizza box and take out the pizzas or whatever, you know. So we can use dynamic obstacles. In this case, that's a dog, but we could use a little robot to make it turn somewhere else. You can use swarms of robots, artificial stop signs, stuff that the human driver would be like, whatever, but the vehicle has to pay attention to. And then the other one, of course, is clobbering, making it fly into something. So this is one of my favorites. It's like this, totally a human driver, but you know, incapacitate the vehicle somehow using map deviations, light vegetation, simulated obstacles at high speed that will cause a drastic and unsafe maneuver. You know, making it run into things like, for example, on an entrance, making it scrape sensors off on the wall or something like that. But to conclude, as the other people take the stage, don't do any of these things. This is just for us to help us design more robust systems. So don't hassle the HOF 9000. Don't hacksaw the bots. Think about these vulnerabilities and how they can inform us to design better systems, more robust systems, and make sure that the evildoers out there can't compromise driverless systems. And then one day maybe we can live the dream of using the empty seats and having the car drive ourselves while we enjoy ourselves in the back seat. So that's it for me. I'm super glad that the demos worked. Thanks again to Kost and Tomer, and thank you very much.